Good morning. Hope everybody's doing well out there, and we're doing good on a Wednesday in this crazy time that we have going on. Want to just say hi to everybody and just welcome everybody to our first video series and live kind of webcast pod, new to the technology. We just wanted to give an opportunity to continue training. There's a ton of training events that are out there, and they're just fantastic. I've been going to them for 20 plus years, and unfortunately, with everything that's going on right now in the country, a lot of those events have been canceled, and it's really there's a gap or a just a big blank spot of opportunity to continue education and to also continue training measurement professionals and really to network and share ideas and pass on knowledge and also gain knowledge. So CRT, we've gotten together and we kind of said, hey, during this time when people have maybe a little bit more downtime than what they're used to, let's try to make it where we can use that to benefit and to help grow and maybe learn from other people too on what measurement's all about. And so we're going to go for the next few weeks and probably even farther on just short topics, 15 minutes to 30 minutes. We're going to go over what's going on with flow computers, what's going on in liquid measurement, what's going on in gas measurement. We're going to try to bring in different vendors to talk about specifically certain technologies. What are their pros? What are their cons? And so we just want you to ask questions. If you have topics that you want to talk about, please let us know. We'll try to get a subject matter expert lined up so we can have some discussions about those. But at the end of all this, we're also going to save these videos and post them up on YouTube, so you can use them as a reference going further. And pretty much any time, we'll get into some specifics down the road of really detailed advanced troubleshooting on equipment and processes and just electrical guidelines and instrumentation guidelines and measurement guidelines. And hopefully these are tools that we can use going forward. So again, if there's any topics that you want to see that we don't have listed, or if you want to present a topic or you want to share this information, please go right ahead. Hey, we want to share the knowledge that some of the people that have passed on to us, and also we want to be able to present those people so we can capture that knowledge and share it to everybody else. So get a hold of us at CRT. If you've got specific questions, there'll be links up on emails and our contact information. And we just appreciate you taking the time this morning to join us. And we're going to go ahead and get started on this. I didn't introduce myself. My name is Brent Palmer. I'm with CRT Services, and I am the manager of measurement technology, which means that if it involves measurement, flow computers, meters, whatever the technology is, we're always looking at new technologies and how to use existing technologies to create accurate custody quality transfer measurement and do it as accurately and efficiently as we possibly can. So we help our customers in doing that. And like I said, we just want to pass on some of our expertise and hopefully create this forum where everybody's going to be able to utilize this information in a constructive way. So as far as the controls and everything goes, if I believe that you can message in this and post messages up with questions, or you can unmute your microphone. When we get to the end, I will have a question and answer session that we can do. But if you have questions that maybe you think of later, hey, shoot us an email. And if I can't answer them, I'm going to get you in touch with a subject matter expert, whether it's with CRT or the manufacturers that can. So again, this is about passing knowledge and learning. And I learn something new every day when I talk to customers and when I talk to other measurement professionals. And, it's a phenomenal industry to be in. And there's a lot of great people that want to help share that knowledge and pass it on. So let's get started. This first module or this first class is going to be an introduction to flow computers. And specifically, we're going to talk about them in liquid use and what they do. So for those people that are new to the industry or don't really even know what a flow computer does, This is going to give you a brief overview and a little bit of explanation and kind of go over some of the things that we do. So I've been involved with flow computers for the last 20 some odd years. I love them, love the ins and outs of them. I think they're really great machines, and we'll go over exactly what we're able to do with those in liquids and how they're used as both measurement devices and also some control devices. So as long as I can advance to the next screen, what is a flow computer? Well, it's a counter. Basically, at its core, what we want to do with this thing is we want to start counting pulses coming from a meter. So we're going to count, we're going to add, and then we're going to present this data at the end of a batch or at the end of a week, an hour, a month, and somebody is going to bill somebody else for the amount of product that went through. Somebody wants to get paid for it, somebody wants to buy it, but we want to make sure that we're doing it as accurately as possible. So it's a recorder. It's recording events that happen within your measurement system, the devices that are connected to it, temperature, pressure, density. You can have chromatographs, tank levels, provers. One of the things that's a requirement of a flow computer is that it records events, it records alarms, it records changes that are made to it either by programming or process conditions, and that they're kept in the flow computer for a certain amount of time in an audit trail, so that if we can go back and look and see what happened, but also possibly make corrections if something went wrong or if something was inputted wrong. And what I mean by that is if I have a temperature transmitter that's flowing at, let's say, 70 degrees, but all of a sudden that transmitter fails to 20 degrees, well, we do a correction on the liquid for the effective temperature. Well, if it was at one temperature that was higher and now it's recording a temperature and correcting at a very lower temperature, the volume that it's recorded is going to be off. Well, we need to go back and make a correction on that. Well, if I don't know when it failed, then I can't really make an accurate correction. So if I'm not recording this in the flow computer, I may have to make a correction all the way back to the beginning. And in some cases, we've got systems where the ticket or the quantity is counted over a month. Well, if I don't record when that temperature failed during the course of that month, my contracts may stipulate that I have to either say that that temperature was all at the whole month or halfway through the month, as where I can actually see the volume in the audit trail when that temperature went bad, and I only have to correct back to that time when the temperature went bad. So it's also a savings, but we want to see what's going on in the flow computers and who changed what, when it was changed, and also events and alarms that happened inside of it. It's an archiver. We want to save data. We have quantity transaction records. So we have batches that we're recording this information. Again, a batch is a movement of product over a period of time, and that time may be all over the place, but we want to see how much volume was moved, and we need to save that in the flow computer. So we're archiving that information. We're putting it and storing it in the flow computer, and API requires that flow computers store this information for a certain amount of time. So we're archiving information. We're a diagnostics machine. Think about the processes and the information that's coming into the flow computer. Well, we've got temperatures, we've got pressures, we've got meter pulses coming in, we've got communications going back and forth. The flow computers you're able to drill into a lot of these and see the status of an input or see the status of a device coming in. With smart devices, Coriolis meters, we're polling for a lot of diagnostic information and bringing that back in. When you think about a flow computer as it sits on a measurement skid or a liquid skid, it has most of the measurement devices directly attached to it. So you're able to perform diagnostics to see how the instrumentation on the whole skid is working, because most everything comes back into the flow computer on these skids. So powerful diagnostics tools that are built into a lot of flow computers out there. I mentioned communications. It's a communicator. It's a device that SCADA is polling to get the flow rates, or that locally a PLC is polling to get temperatures and pressures, flow rates again to control flow. So we're getting this on SCADA systems. We're passing this information via Modbus or Ethernet IP, or we're putting it in SQL databases and passing it on to accounting systems. Locally, again, the PLCs are talking Modbus to it and pulling it for process information so they can go ahead and do their control. Or we're pulling other devices, tank gauges, smart meters, Coriolis meters, ultrasonic meters, and bringing diagnostics information or process information like density off of these meters. So it's a communicator. It has to be able to communicate with a lot of different devices and a lot of different protocols. And it's just a really cool device. I think flow computers are one of the coolest devices out there. PLCs are boring. They have ladder logic and you know, they do the same thing over and over and over again, but they really, you know, they upgrade, they start a valve, or they start a pump, they stop a pump. They open a valve, they close a valve. These things flow computers do complex calculations and record keeping and printing reports, just all kinds of cool things that PLCs typically aren't doing. So I think they're cool devices. So in a typical liquid measurement system, you have all these different components. You've got a SCADA system, which is, let's say, where the controllers are, and they have a front-end system where they're seeing process information come back from the flow computers. You've got valve control logic, which is typically inside of a PLC, so it's opening and closing valves into systems or in and out of tanks and so forth. You've got a batch controller, which is basically controlling how much is coming through on a particular system. You've got PID controllers, so you're controlling flow rates, you're controlling pressures, you're controlling back pressures on a system. You've got a prover controller. So you've got a prover, which is out there, and these are the devices that are used to calibrate meters, and there's controls that are behind them. You've got your flow computer, and then typically you had a separate sampling controller system. So all of these was an accepted philosophy was to put all of these systems separately. But now what we find is flow computers can do a lot of this function built into one device. So I don't have to have a separate sampler controller, and I don't have to have a separate PID controller to control back pressure and flow rate. And I don't have to have a separate PLC system to come and get the SCADA front end information. So there's just a lot of things that we can build into a flow computer, or we can use a flow computer simply for the volumetric calculations. But there's some complexity in them now that allow them to do a lot of other controls without using just other devices that are out there. So now we're taking all these systems and sequencing and data logging and communications, and we're bringing them all into the flow computer. And with that, again, we're going to one device. We have secured, authorized access into that device, and we're able to access it a lot of times remotely across SCADA systems or across network systems, and get into these flow computers and actually have one device that is the edge gateway for everything that I have on my system. So a lot more complexity and functionality has built into flow computers over the years. But you still have the option of just saying, you know what, I want this just to be a flow computer. I don't want it to do valve control, batching controlling, sampling controlling. These are all functions that I have other devices for. I want the flow computer to count and correct. So there's some compelling reasons for new technology and looking at the new opportunities that flow computers are able to bring. As meters have become more intelligent, we have all this diagnostic information that we're able to get off of a meter. Before, we were typically using displacement meters, or we were using turbine meters, and we see a pulse coming in from the meter, and we're counting that pulse, and then we're turning that pulse, that count, into a volume, and we're correcting it based upon temperature and pressure inside. But when something happens, we don't really know why it happened. Why is my meter over-registering? Why is it under-registering? Well, as we've started to get into new technologies, one of the cool things about it is, let's say a Coriolis meter. Well, Coriolis, because of the process that it takes, there's a lot of diagnostics information inside. So we're actually able to pull and see drive gain, tube frequency, the harmonics of the meter, and use that information to see where processes may be failing. One of the things that we're able to see quite easily inside, let's say using a Coriolis meter, is that we may have entrained gas in the system. I'm not holding enough back pressure. Well, the drive gain and tube frequency are going to show me when I have issues with, let's say, the volumes not going correctly because of air in the system or gas in the system or slugs of water coming through. I'll see the density change. So we're able to use this advanced diagnostics and bring that back in and use it in ways with newer flow computers that historically we weren't able to do with just simplistic counter boxes. So the quality of them has increased. As electronics have changed over the years, the availability of higher speed processors, more additional memory, and more reliable technologies have come along. So, your flow computer of 20 years ago is not what is available today or even 30 years ago. And the integration into supervisory software systems, we're able to bring in more than just 20 pieces of data now. When you look at some of the flow computers that are out there, you have tens of thousands of pieces of information that are available. And typically off most flow computers, we bring back temperature, pressure, density, flow rate, and some totals. There's a wealth of information that doesn't come back in. And we're looking at that more and calling that measurement data as opposed to just your typical SCADA data that may be out there of just bringing back this normal process information that we would see on a pipeline, flow rate, temperature, and pressure. There's just so much more data that we're able to get out of today's systems. The other thing that we're able to do with flow computers is also create virtual flow computers on top of flow computers. So we're able to take a flow computer that may be out there and run a software flow computer over top of it and check for mismeasurement issues on the primary flow computer or groups of primary flow computers. So it's a backup system. We don't see it too much in the US, but globally, redundant flow computer systems a lot of times are mandatory. You're not just going to put in 1 meter and one flow computer. You're putting in 2 meters and 2 flow computers in case the one flow computer fails or the 1 meter fails, that you always have a backup system to take over immediately. These systems are critical, or we're using it as a verification to basically say, well, this meter said that I gave 1 barrel, but this flow computer is saying, no, it was 0.9 barrels. Why is there a discrepancy between the two? Did something happen on the primary? Do I have a calibration that's out? So secondary source for mismeasurement information is also a really important function that these next generation of flow computers can do. And I spoke briefly about mismeasurement management, but it's a way for a flow computer and a virtual flow computer to do comparisons, to have redundant measurement, to have high and low limits on process values, to bring back your alarms and events and store them in other information. Remember, a flow computer does have a finite amount of data storage inside of it. If I'm able to bring that into a mismeasurement management system, then that information goes from being stored locally for 30 days or 6 months, depending on the amount of storage space that you have in the flow computer, to now it's stored for decades or whatever your data retention policy is within your company. So the longer I can go back and pull up an issue within a flow computer, the more data that I have in maybe a dispute for a custody transfer that we're in. So I'm able to go back and look back a year and see what happened at the system or see a batch and so forth within there. And we're also able to do trending and various other things within these mismanagement systems. So what are the roles that we typically see within a flow computer? Well, you've got an operator. What's an operator doing? And pretty much a lot of different things. What we found within systems is that an operator at one company or at one area may not be the same as an operator in another area. So I may have an operator that the only thing that they do is they look at the flow rate, and maybe when the report comes out, they pass the report along, or they make sure that a batch ended at midnight or 7 o'clock in the morning. But other operators may actually have to go in and do proving and change meter factors and do some little bit of diagnostics. So we look at the roles inside of a flow computer, and we try to create displays and also access limits based upon these specific roles. So the roles that we can have, again, are an operator. Well, I may have a prover, just a person whose function, a technician whose function is to come in and just prove those meters and implement new factors and do some calibration on the system. A balancer, they're coming into the flow computer and they're pulling out reports, or they're coming in to get reports to verify the data that they have, and they're balancing pipeline systems, or they're balancing the accounting system, the volumes that are recorded, or they're balancing and they see an error in the system and they need to get into the flow computer and figure out why we had this error. So they're going back and look at the audit trail to figure out, oh, we did lose temperature. Now we need to make a change. Our technicians, they're troubleshooting, they're installing, they're verifying the instrumentation, doing calibrations on the instrumentation. And a technician in one facility may be also the measurement person. So they're going through and they're programming the flow computers up. In other cases, no, they're just technicians, and they'll do the wiring and they'll do the calibrations of the instrumentation, but they're not actually into the flow computers doing any programming on it. Probably the most dangerous person within a system is the manager. They're the ones that we definitely don't want to get into the flow computer, because they're the ones who think that they know about being a technician, a programmer, and everything else. And they're the ones who just really need to look at information, help direct policies, and just verify that those policies are followed. And I joke about managers, but I've had a lot of great managers over the years, but I always ask them not to get into flow computers. Just tell me what you want, and we'll get in and get the information or make the changes for you. Accounting, they may be looking at reports. Again, SCADA, it's getting information back out, or they're doing controls in it, so they're issuing batch ends from the SCADA system, or they're getting into the flow computer to issue a batch end. A customer, you may have your device at a customer's facility. So the customer's walking by and is able to pull out their reports, or your reports are printing out locally for a customer, or they're pulling your flow computer for information. Engineers, that could be programming engineers that are getting in and programming the flow computers, or they're helping to design the control cabinets and the systems, or they're designing the whole system, and they need to be able to get in and look at some of the processes that they're going through. And the last one is the programmer, the guy who knows what they're programming in the flow computer. I talked about the sheer number of parameters that are inside of a flow computer, and the data that's inside of there. We have to have an understanding of not only instrumentation and communications, but you need to understand basic measurement and measurement in general to make sure that you're selecting the proper tables and K factors and meter factors, and how you're handling equilibrium vapor pressure, and just a lot of other functions that are specific to a flow computer that aren't in a PLC, that aren't in an IT system. So there are professionals out there that program flow computers and get them to do what a company needs to do. So that's roles that I see within the flow computer, and there may be other roles that are out there that I haven't identified in there. So, and why do we have all these roles? Again, when we look at this is just process inputs into a flow computer to determine, this is taking the volume pulses with density and temperature, and how we actually turn around and take that temperature, pressure, and the pulses coming in and produce gross barrels, net barrels, mass barrels, or not mass barrels, mass pounds, and turn them also into flow rates. But it's how we use the tables, how the tables convert out, and each step along the process of going in and coming up with an actual corrected volume. So they're pretty complex processes inside there. Flow computer security is extremely important. Who has access to your systems? Does it log changes? Does it define the user roles? Are we able to have just one password in our flow computer? Who's into it? Do you allow everybody just to go into your PLCs or to go into your IT systems? Flow computer security is something we take very seriously. I take very seriously, because we want to provide secure access to a device. We don't want to give people access to something they don't need to have access to, and give them the opportunity to make a mistake. Not necessarily do I think that people are malicious, will go in and do something to mess with it. It's just sometimes people make changes that they're not aware how it impacts a change within the system. So let's control flow computers, and most flow computers have a way of putting security on them and to control the access within them. Should you have remote access? Well, I think as we get into what we're doing now, remote access is highly important into flow computers. I know the IT people usually discourage it, but if you can get into a flow computer right now that's sitting in Wyoming, that's coming off a lag skid, and troubleshoot what's going on with it, I can't get on a plane really easily right now and get out there. So I can troubleshoot something in a matter of seconds if I can get into the flow computer remotely, as opposed to having going out there. And there's some great solutions out there. We have a partner that we work with, Samsara, that we're able to provide remote solutions with just a black box that we can set up immediately and provide outside of the IT environment that you're currently in, a way to get in there. So there's solutions that are available today to get right into some of those devices that you may have access, don't have access to, but need it immediately. Analog communications, basically what this means is if I'm taking a temperature in and it's an analog signal and I'm able to communicate with the transmitter and bringing it on as a communication signal instead, what are the benefits and cons to it? Well, the benefit is with an analog signal, typically I have to have a scaling to it. I have to know what 4 milliamps is that 20 degrees? And I have to know what 20 milliamps is that 200 degrees? So if my transmitter is scaled incorrectly, or the scaling in the flow computer is scaled incorrectly, I can have a mismatch there. Plus, I also have to calibrate that analog loop that's coming in. If they're smart, HART, Modbus, I can just pull the process value. I don't have to worry about scaling, because if I'm just reading a register inside the transmitter and the transmitter says it's 50 degrees and I pull that register and it says it's 50, I don't really care if the analog signal's off a little bit. I know that it's 50 degrees. I don't have to worry about scaling on my side. So the downside to it is if we lose communications, you're not updating your process value. So, and again, I'm going to ask, 1Password, is it enough to have in your flow computers, or do you need to define? I bring this up a lot because, again, security and authorized access in the flow computers is very important. Density, I'm just going to mention it real quick. In liquids, one of the biggest effects of our volumetric corrections is density. I call it a friend or a foe, but if your density is not right, if you're not calibrating your density, if you're not verifying your density, if you don't know what density is and you're programming flow computers, you really needed to find out, because density is the basis of your corrections in the flow computers, along with temperature and pressure. And it has a huge impact on the volumes that you're billing for. Calibrations, how often should you do them? Pretty much every time I think you're out there. If you verified your meter and it's off, or verified your instrumentation and it's off. So do calibrations frequently and often. I just wanted to show, I think this is one of the coolest pictures that I have. This is a detector switch, and this is from approving, and this is what a detector switch looks like when the ball goes past it. And the detector switch at the end of this kind of does what we call slap. It creates this signal on the outlet of or basically when the ball goes by, it travels at such a high velocity, it creates this little slap. And then this is what we can see inside the flow computer that can also cause a miscalibration. Audits of your flow computer, you should have a good auditing process. You should do it as often as you can. Come up with a normal or an interval where you're auditing the flow computers, pulling out the audit trails, looking through what happened inside them, and doing it on a frequent basis. Some of the companies I've worked for, we typically would audit flow computers at least once a year. And it doesn't have to be a complex audit. You can do generic audits where you're just verifying, do I have the right weight of water? Am I using the proper tables? Have I had the correct density coming in, and back pressure calculations and equilibrium vapor pressure tables? So it's just going through and looking at a few things, and then maybe pulling up the audit and scanning through these audits to look and see if that there's processes or something was changed that we didn't need to have changed in there, and then looking at all the parameters. So very important to do. And that is the end of this first session. We're going to be doing another one here in about a half an hour that's going to go over liquid calculations, how we come up with from start pulses coming in to how we end up with our final volume and what affects that. Are there any questions that anybody may have? All right. Oh, I'm sorry. Go ahead.
I'm sorry. Yeah, can you hear me?
Yeah, we can.
Brent, I'm new with pipeline, so I'm learning as much as I could on Spirit. So I really appreciate that you put this training together.
Well, thank you.
And I'll be glad to follow up on all this training.
Okay. Yeah, we actually have. We're going to get into more specific training on some of the manufacturers. The FlowX by Spirit ABB. We'll get into doing some Omni training and some other training for other devices that are out there. This is just the kickoff. Like I said, this is something that we're going to continue doing, and we'll continue with different series. And as our crisis starts dwindling down, hopefully in the time to come, that we'll also continue doing this and continuing these video seminars as a way to just inform customers and also drill maybe into more detail about how to do specific process information. So really appreciate it. We'll, where you saw the class schedules, we will provide a YouTube link for this video when it's done. So please, again, pass them on, and we'll send out updates on where these videos are going to be. So hope everybody has a good day. Stay safe. Again, if you guys need any help, please give us a call at CRT, and visit our website for updates on when the training will take place and the links that we provided out. And just want to thank everybody for coming. Have a good day.